So regularization techniques or penalized regressions. Penalized regression techniques is one of the important things you need to understand here. Now, these techniques are important to tackle the problem of overfitting. The classic problem of overfitting, which is the model performing well on trained data, the model performing very bad on the test data, or the model performance will be very bad when you repeatedly test with the same data. That problem we call it as overfitting problem. Regularization techniques will help us in this overfitting problem. This is one of the common questions. Regularization prevents the overfitting. Regularization prevents the overfitting by adding extra information or a penalty. Generally, penalty, we use the thing called lambda. Penalty referred to as lambda to the regression. So by adding extra information or a penalty to the regression, it reduces this overfitting. So basically, it shrinks the coefficients to 0 or close to 0. It shrinks the coefficients to 0 or close to 0. Okay. Now, regularization works by adding a penalty or a complexity term or a shrinkage to the residual sum of square model, to the residual sum of squares model. That means these techniques work after initially building a regression model. When will you get this sum of squares of error? After building a initial regression model, you will get the coefficients. Once you get the coefficients, you will calculate the predicted values. Once you calculated the predicted values, you will get the residuals. Then you sum square residuals and sum square error will be calculated. On that sum square residual and error, the coefficients, this penalty will be assigned. This penalty will be assigned. Okay. Now, there are three types of regularization techniques. The first one is called as Lasso. Lasso regression. Lasso means least, absolute, and selection operator. Lasso means least, absolute, and selection operator. Also called as the L1 norm. Also called as the L1 norm. L1 norm. Now, Lasso adds a penalty or lambda, typical lambda or penalty is added, or lambda is added to absolute weights or coefficients, absolute values of the weights or coefficients. Absolute weight. Lasso will make sum of the coefficients 0. By default, Lasso will make sum of the coefficients 0. If the coefficient becomes 0, will it have an effect on the dependent variable? No. So Lasso also works as a variable or feature selection method. Since it makes sum of the coefficient 0, if you give x number of variables, Lasso will return x minus. That means you will get lesser variables compared to the given variables, because it will make some variable coefficients 0. It will make some of the variable coefficients 0. So this is one of the way of feature selection or variable selection. Lasso works as a feature selection method or a variable selection method. So it will make some coefficients equal to 0. That will happen. Okay. Typically, those coefficients which are very close to 0, it will make them 0 by adding the penalty. Okay. So that we call it as the Lasso. Lasso is one of the most popular feature selection model. Lasso does not work well on multicollinear data. On some of the multicollinear data, Lasso will not work properly. Okay. Now, if you are looking at the Lasso equation, the cost function, so this is the objective of Lasso. Alpha is the penalty. Alpha is the penalty. Sum square, regression sum square object. And the equation is, and you have to be very careful with the alpha values also. How you give alpha values in Python, that also is very important. If alpha is equal to 0, you will get the same coefficients back. It will not do variable reduction. If alpha is set to infinity, all coefficients will be made 0. If the alpha is between 0 and infinity, you will get coefficients that of a simple linear regression. So you have to give alpha between 0 and infinity. Alpha of 1, 2, 3, like that you have to give in Lasso. The alpha has to be greater than 0. It can be 0.05, it can be 0.10, it can be 1, some data points, it will be 2 sometimes. So it will be based on the data points which you are dealing with. Now the equation, the function is this. There is a Lasso function. This is the context of Lasso. Absolute y minus beta into x square plus lambda into absolute value of the coefficients. This is the Lasso equation. All right. Got it, all of you? L1 norm and Lasso. L1 norm and Lasso. The next is ridge. Ridge regression, or also called as L2 norm, adds the penalty or lambda which multiplies with the sum square weight of, or with square weight of each variable. With squared weight of each variable. The penalty term regularizes the coefficients of the model and shrinks the coefficients into smaller values or closer to 0, but not 0. So ridge cannot be used as variable. Ridge cannot be used as variable or feature selection technique, because it will not make any of the coefficients 0. It will bring them closer to 0. It will reduce the size of the coefficients, but it will not make any coefficient 0. So ridge cannot be used for variable or feature selection. Lasso will by default reduce the variables. Lasso will do the by default reduction of variables, but ridge will not do. Okay. Now, ridge is used when we have multicollinearity in the data. If you have multicollinearity in data, then we will use ridge regression. If you have multicollinearity in data, then ridge regression can be used. So ridge regression, if you are looking at the formula, this is the formula. You multiply lambda with the coefficients. You will multiply lambda with the coefficients. Why this thing is stuck here? With the coefficients, not other coefficients. These two are based on coefficients, not others. Coefficients. Yes, not the others. This penalty is applied on the coefficients, betas. You see the equation, right? Beta. It is not errors. It is done on the betas or the coefficients. Trying to interrupt the kernel, it is also not interrupting. See, the difference is square. See, here the lambda is multiplied directly by the coefficient. Here it is square of coefficient. If you see here, square. That is the difference. Here it will take the absolute value of the coefficient. Absolute value means it will ignore the negative signs. Here it will square the coefficients and then the lambda will be multiplied. Got it? Then there is a third type of regression called Elasticnet, which is a combination of L2 plus L1 plus L2. The third option is Elasticnet. Elasticnet is a combination of L1 plus L2. That means first it will run the lasso, and on lasso output it will run ridge regression. Elasticnet is, there is no space, Elasticnet is L1 plus L2. Let's just me confirm, Elasticnet is L1 plus L2. So first it will run lasso, then it will do the ridge. Or what will it do? First Elasticnet, right? So linear regression with combined L1 and L2 priors as regularizer. First, lasso will be run, and on lasso output, ridge regression will be run. So Elasticnet can be used as a feature selection technique. Elasticnet works as variable selection, variable or feature selection method. Elasticnet. It's a combination of L1 plus L2. First, lasso will be run. On the output of that, what you call as ridge regression will be run. So you can see here, sklearn linear model, linear regression combined with L1 and L2 priors as regular. Minimizes the objective function alpha into L1 ratio plus 0.5 into alpha into L2 ratio with the squared weights. So alpha value will range from 0 to infinity. If you give alpha is equal to 0, it will run normal regression. So alpha cannot be 0. It has to be greater than 0. So regularizations, penalized regressions or regularization techniques are important in multiple linear regression. They are also very important in neural networks. These penalized regularization techniques in regression and neural networks. Okay. See, if interviews they ask what is the difference between lasso and ridge, you simply say lasso reduces the number of variables by making coefficients equal to 0. Ridge will reduce the size of the coefficient but not make them 0. Second difference is lasso is applied on absolute value of the coefficients. Ridge is applied on the squared value of the coefficients. These are the two differences we just talk about when we talk about regularizations. And why do we need to use regularization? To avoid overfitting. To avoid overfitting, regularization is used. No, classification also, no, binary logistic regression. Classification also binary logistic regression. And I think in a support vector classification also there is a L1 penalty. SVC also has an N1 penalty, right? See, support vector also has penalty. Support vector has penalties. So if you say penalty, logistic regression, you have penalty because that is also regression. Lasso is penalty. And then neural networks will also have penalty. So here alpha, see. So alpha here is, so you will see this alpha, wherever you see the alpha, that is a regularization. In SQL and Python, we call it as alpha. In sklearn, alpha you see means that is talking about regularization. Here, L2 penalty is by default in neural networks. L2 is by default in neural network. Default is 0.0001. The alpha value is 0.0001. So you will see regularization or penalization in multiple linear regression, binary logistic regression, neural networks, and support vector machines. And in Python, we refer to it as alpha, which is nothing but the penalty or regularization term or shrinkage term. Different textbooks use different thing, but penalty, lambda, or shrinkage or alpha means same thing. Alpha, lambda, penalty, or shrinkage, they are all same. So on this data, you can run house prediction data. If you want, you can run Lasso, Ridge, and Elasticnet. sklearn has separate Lasso. So you have this Lasso. Alpha is by default 1. Similarly, you also have Ridge and you also have Elasticnet. You can run these models on house price data and you can see how the output goes. Try running Lasso. sklearn.linear_model, import Lasso. Let it be default alpha is 1. from sklearn dot linear underscore model import L capital Lasso. L1 is equal to Lasso. L1 model is equal to L1 dot fit x comma y. L1 model dot score x comma y. It is 85.43. Right? Now you can see the coefficients. L1 model dot coefficient. P dot round L1 model dot coefficient comma decimals is equal to 2. Some of the coefficients are 0. You can see here. Decimals is equal to 5. How come decimals are not reducing 10? Is equal to 2. Equal to 1. But we are not able to see the coefficient zeros. Print list with x dot columns comma L1 model dot coefficient. Now we got the coefficients in proper way. Which of those coefficients are 0? I don't know why we are not able to see the coefficients equal to 0. Some of them will be 0. Like how it is told in the documentation. Or L1 model dot sparse coefficient okay. From sklearn dot linear underscore model import rich. L2 is equal to rich. L2 model is equal to L2 dot fit x comma y. L2 model dot score x comma y. 8543. Print list zip x dot columns comma L2 model dot coefficient. So we run the ridge regression L2 model. So L1 is lasso, L2 is ridge, and Elasticnet is combination of L1 plus L2. Similarly, from sklearn dot linear underscore model import Elasticnet. N is equal to Elasticnet. En model is equal to En dot fit x comma y. Oh, maximum outer iterations have reached. Okay. Max underscore iter is equal to 1000. Oh, 5000. Objective did not, you might want to increase the number of iteration. So make it 10,000. Still it is not working. Make it 30,000. Still it is not working. 1,000. Consider increasing regularization. So alpha is 1. So other things. Increasing regularization. Alpha is 0.1. L1 ratio is 0.9. We'll use this one. Still, it is not converging. I think we have to scale the data. That is the only option. Right? So we'll stop here and we'll continue in the next session. I've sent you the files.